Dear students, in this session, we will try to arrive at a relationship between the boundary layer thickness delta and the Reynolds number. So let us try to find a relationship between these boundary layer thickness and the Reynolds number. Similarly, the shear stress and the Reynolds number, as well as the drag coefficient and the Reynolds number for a flow over a flat plate. I will repeat once again. Now let us consider a flow is going to happen over a flat plate. So it's a real fluid. A boundary layer thickness will be formed. So what will be the relation between this boundary layer thickness and the corresponding Reynolds number? Similarly, what will be the relationship between the Reynolds number and the shear stress, namely the tau naught, as well as the relationship between the coefficient of drag and Reynolds number for the velocity profile in between the boundary layer. For example, now this is the boundary layer. This is the boundary layer thickness delta. Here the velocity is going to vary. This variation is called a small u, and the velocity at the boundary is called as free stream velocity, namely u or u infinity. So now we can see, we can give a velocity profile between this small u by capital U. That is a variation of velocity within the boundary layer to the free stream velocity capital U. Let us give this expression as 2y by delta minus y squared by delta squared. So for this particular boundary condition or for this particular velocity profile, let us try to arrive at a relationship between the delta and Re, as well as tau naught and Re, as well as CD, that is coefficient of drag and the Reynolds number. So I hope the problem is clear. When the flow is happening over a flat plate, when the velocity profile u by u is given as 2y by delta minus y squared by delta squared, we are going to arrive at this given expressions, the relationship between these expressions. Dear students, let us continue further. Let us try to derive the value of tau naught from this one Karman boundary layer equation. We will try to establish the relationship between delta and Re. So where tau naught is the shear stress, rho is the density of the working fluid, u is the velocity, that is free stream velocity, and theta is the momentum thickness. Okay, so theta will be equal to, we know the formula, 0 to delta u by capital U into 1 minus u by capital U dy. In the last session, we have derived this equation. We try to substitute the value of u by u from this equation, and we try to get the value of theta in terms of delta. So what is u by u? So u by u you can substitute from here. So theta will be equal to what? 0 to delta 2y by delta minus y squared by delta squared of 1 minus 2y by delta minus y squared by delta squared the whole square of dy. So if I'm going to substitute and when I'm going to integrate, I'll finally, after simplification, we'll arrive at theta equal to 2 by 15 of delta. This one we will derive at the end of the session, but right now we'll make use of this value and try to substitute over here. So this one we already did in the previous session. If you have any doubts, you please go to the previous session, or at the end of the session, I'll derive once again how we got theta equal to 2 by 15 delta. So let us now try to substitute 2 in 1. So substituting 2 in 1, we get tau naught by rho u squared is equal to t dou by dou x of 2 by 15 delta. So here 2 by 15 is a constant, so we can take out of the differential operator. So tau naught by rho u squared is equal to 2 by 15 of dou delta by dou x. Where delta is nothing but your boundary layer thickness. Let us have this as equation number 3. So I will erase and I will try to retain this equation alone. So now we have obtained an equation called as tau naught by rho u squared equal to 2 by 15 of dou by dou x of delta. As well as we know the general formula for the shear stress, which is given by tau equal to mu into dou u by dou y. This is for any fluid which obeys the Newtonian law or the Newtonian law of viscosity. So the corresponding fluid will be called as what? Newtonian fluid. Okay, that's fine. So we got tau equal to mu into dou u by dou y. We want what the shear stress at the wall, near to the wall. So it will be called as tau w or tau naught, which will be given as mu into dou u by dou y at y equal to 0, because we want the wall shear stress. So the wall shear stress can be obtained when the y becomes 0. So when y equal to 0, we are trying to find the value of shear stress, that is wall shear stress. Okay, fine. Now we know u by the philosophy is what? U by u equal to 2y by delta minus 2y squared. I'm sorry, it is y squared by delta squared. So you keep u alone here. So it will be capital U of 2y by delta minus y squared by delta squared. So I'll differentiate this u with respect to y. So it will become dou u by dou y is equal to u of 2 by delta minus 2y by delta squared. Now I want dou u by dou y at y equal to 0. So what will happen? This term will become 2 capital U by delta. This term will become 0. Why? Because y is 0. So this term vanishes. So we got now dou u by dou y at y equal to 0 is what? 2u by delta. So substitute this value here. Let us call this equation as equation number 4. Let us call this equation number 5. So substituting 4 in 5. Substituting 4 in 5. So tau naught will be equal to mu into 2u by delta, or I can call tau naught equal to 2 mu u by delta. So this is another expression. So let us call this expression as what? 6, and the previous expression this is what? 3. So now what is the idea? You will try to substitute the value of tau naught in this expression. Substitute 6 in 3. So I will recall once again what we are doing. We are making use of the one carbon boundary layer equation, which is given by tau naught by rho e squared equal to dou theta by dou x. We have already known the value of theta in terms of delta in the previous section as what? Theta equal to 2 by 15 delta. So I am trying to make use of that equation and obtain the equation tau naught by rho e squared equal to 2 by 15 of dou by dou x of delta. This is one equation. Now let us try to come from the basic fundamental principle of Newton's law of viscosity, tau equal to mu into dou u by dou y. Now I want the wall shear stress at y equal to 0. So tau naught will be equal to mu into dou u by dou y at y equal to 0. So when I obtain this one, I end up with what? Tau naught equal to 2 mu into u by delta. Now try to substitute this value of 6 for tau naught in equation number 3. We'll almost end up with the solution what we want, the relationship between delta and Re. Let us do it now. So we can see here, instead of tau naught, I can put as 2 mu u by delta of rho u squared, because this rho squared already is the denominator, equal to 2 by 15 of dou delta by dou x. So this 2 get cancelled. So I'll end up with what? 1 u and 1 u will get cancelled. So it become 15 mu by rho u will be equal to delta into dou delta. This dou x can be brought this side. This dou x can be brought this side. So let us try to integrate on both sides. So integrating on both sides, this side with respect to x and this side with respect to delta. So it will become 15 mu x by rho u, okay, equal to, this side will become delta squared by 2 plus a c. What is c? Because it's indefinite integral, we do not know the limits of integration, and hence it includes plus c. Now let us try to find the value of c. It is the flat plate. When the flat plate is there, at this point x equal to 0, isn't it? At the beginning point, at the leading edge, let us call this leading edge as A. Now this is the boundary layer growth. Now at x equal to 0, what will be our delta? Delta will also be equal to 0 because there is no boundary layer formation. So at x equal to 0, delta equal to 0. So I am substituting this boundary condition, then 0 will be equal to 0 plus c, which means constant equal to 0. So invoking c equal to 0 in this equation, I will end up with delta squared equal to 30 mu x by rho u. Okay, just I cross multiplied. I used this equation and I made c equal to 0. So delta squared equals 30 mu x by rho u. Now you multiply x in the numerator and denominator. So delta squared will be equal to 30 mu x into x by rho u into x. So it will become what? 30 mu x by x squared into rho u x. That was I multiplied and divided by the value of x. So the value doesn't changes. And I'm going to bring this mu also denominator. So it becomes 30 x squared by rho u x by mu. So what is the left hand side is delta squared. So delta squared will be equal to 30 x squared by, what is this term? It's nothing but rho v d by mu. It's nothing but Reynolds number with respect to x because the variable is x. Okay, so it's a, I don't want delta square, I want only delta. So when I'm going to take the square root of 30, it will become 5.48. X squared will become x and Reynolds number will become the square root of Reynolds number. So this is the relationship between the Reynolds number and the boundary layer thickness. So the first step we have arrived. We have arrived the relationship between delta and Re as delta equal to 5.48 into x by square root of Reynolds number with respect to x. So in a further we'll continue and try to establish the relationship between shear stress and the Reynolds number as well as the coefficient of drag and the Reynolds number. On continuing further, let us now try to arrive at the relationship between the shear stress and the Reynolds number. So already we know that we have earlier derived that tau naught equal to 2 mu u by delta. Now substitute the value of delta over here, we'll end up with tau naught and Re. That is especially what we want. We want the relationship between tau naught and Re. It's very simple. So it will become 2 mu u. What is delta? 5.48 x by Reynolds number based on x. Okay. So when I'm going to divide 2 by 5.48, it will become 0.3649. We'll round it off to 0.365 mu u by x, and the square root of this term will go to the numerator. So it will become what? Reynolds number x. So now we obtain the second relationship also. What is the second relationship? Tau naught equal to 0.365 mu u by x into square root of the Reynolds number based on x. Okay. So we will write this expression also here. Tau naught equal to 0.365 mu u by x into square root of Reynolds number. Okay, so this is the one what we got. Now let us go to the third part that we want to arrive at the relationship between CD and delta. CD is nothing but a coefficient of drag and the Reynolds number, namely Re. Okay, fine. So what is CD? The coefficient of drag is given by Fd by half rho u squared. What is delta Fd? Delta Fd, that is the drag force over the elemental length. The drag force over the elemental length is given by tau naught into B into delta x. Okay, so let us try to first find the value of Fd and substitute here. Then we'll simplify to get the CD and we'll finally end up with the relation between CD and the Reynolds number. Okay, what is tau naught now? You substitute from here. So it is 0.365 mu u by x into B into Reynolds number. What is Reynolds number? It is rho capital U into x by mu into B into delta x. This delta x. Where delta is nothing but the, if you want I can recall you. This is the small elemental length is nothing but what? Delta x. The whole length is called as what? The capital length L. So you should know this is the trailing edge. This is the trailing edge. This is nothing but delta x. So now I hope you could recall what is meant by delta x, and B is the breadth. So in this dimension, this is nothing but the breadth of the flat plate. Okay, I hope you can recall those fundas. Okay, now this x can be, the denominator x can be written as what? Square root of x into square root of x equal to what? x. So I can write the denominator as what? Square root of x into square root of x. So what happens means this one square root of x and this one square root of x, because this x is within the square root, will get cancelled. So it will become 0.365 mu u by square root of x of rho u by mu into b into delta x. Okay, so now I don't want the drag force only for the elemental length. I want the drag force for the entire length. So we want to integrate from the limits 0 to capital L. 0 to what? Capital L. So I want from FD, from delta FD, I want FD. So what I will do? It will be integral of the same value. 0. What is the limit? 0 to L. 0.365 mu x, mu capital U, let it be rho u by mu. This x is the denominator, which means x power half. When this half, x power half is taken to the numerator, it will become what? X power minus half into b dx, b in delta x. Still I have not integrated. I have taken the square root of x as what? X power half. When it's taken to the numerator, it will become what? X power minus half. Still I have not integrated. Now I am going to integrate. I will tell what is the value. So when I am going to integrate, it will become 0 to L. I could not put it because I am going to integrate. So 0.365 mu remains same. U. This also there's no disturbance. Rho u by mu. This will become x power half by half. I hope you know the concept. X power n will be integrated will be giving us x power n plus 1 by n plus 1. So x power minus half will become x power minus half plus half. So that will become x power plus half by 1 by 2 into b. Okay, so we have integrated this one. So the limits is what? From 0 to L. So it will become what? It will become what? This 1 by 2 when is taken to the numerator, 2 into 0.65 will become 10, 1. So 2 into, I want to just multiply 0.35 into 2. So 10, 1, 12, 13, 1, 2, 6, 7, 0.73. So it is 0.73 mu u. This will become what? Rho u. This will become L power half because I have substituted the limits. So L power half is nothing but square root of L. So I can take it inside. So rho u L by mu into b. There's no need to apply the lower limit because the lower limit is 0 only. I hope you got it. How we got L? Because it's L power half. When this L power half is nothing but what? Square root of L. So I can take this L square root of L inside this bracket. So it becomes rho u L by mu into b. Okay, fine. So we now got FD. It's not called as delta FD. It's called FD because we have integrated for the limits 0 to capital L. So let us try to substitute the value of FD in this equation. So substitute for FD here and thereby now I'll go. This is the FD. So try to substitute over here. So this will become what? CD equal to FD by half rho. What is A? A is nothing but what? B into instead of delta x, it is the whole length. B into L into u squared. So this 2 I am going to multiply with the 0.73. It will become 1.46. It will become this b get cancelled. So 1u and 1u get cancelled. So the denominator will become rho u L. This mu will come denominator. I will write one more step. This is nothing but this one. So this is nothing but what? Reynolds number based on L. Reynolds number based on L. So one more step I will write. Now what you are writing is nothing but CD only. It's not FD, CD. So CD will be equal to 1.46. This is nothing but what? Rho UL by mu of square root of REL. So CD will be equal to 1.46 by this is REL. This is what? REL. Let us continue further. So let us now take the last profile. U by U is given by 2y by delta minus y square by delta square. Here use the variation of the velocity of the y direction, and capital U or U infinity is the free stream velocity, and y is the distance along the y-axis, and delta is nothing but the boundary layer thickness. To start for this particular case, let us try to revoke the von Karman boundary layer equation. The von Karman boundary layer equation is given by tau naught by rho capital U squared equal to dou theta by dou x. So we are going to make use of this von Karman momentum integral equation for deriving this relationship, where we know tau naught is the shear stress of the wall and rho is the density of the working fluid, U is the free stream velocity, and theta is the momentum thickness. So we know the momentum thickness theta is given by 0 to delta U by U of 1 minus U by U into dy. Already we have, in the last session, we have arrived at the value of theta and delta. So we can see in the last session, we have derived theta equal to 2 by 15 delta. Even then we will derive today also. But if you are already aware of this value, you can proceed to the further steps. But I am going to derive how we are going to establish theta equal to 2 by 15 delta. And after getting this value, I will substitute for this von Karman equation. Okay, fine. Now let us take this theta. I will do it fast. So I am going to multiply inside. So U by U minus U squared by capital U squared of otherwise, let us try to substitute the value of this U by U. So U by U is given by this value. So 2y by delta minus y squared by delta squared of 1 minus the square of this value. So 2y by delta minus y squared by delta squared, the whole square of dy. So before multiplying this one, let us simplify this term. So it will become 0 to delta 2y by delta minus y squared by delta squared of 1 minus 2y by delta plus y squared by delta squared of dy. Here is 2 terms, here is 3 terms. So when I am going to multiply, there will be some 6 terms. That's it. Then you integrate, substitute the values of limits of integration, you will get the solution. Okay. So first I will try this term and I will multiply with all the 3 terms. Okay. So please tell me if I make any mistakes. So it will be 2y by delta minus 4y squared by delta squared plus 2y cube by delta cube minus, now I am going to multiply by this one and this one. So it is minus y squared by delta squared plus 2y cube by delta cube plus, it's not plus, it's minus y power 4 by delta power 4. Still we have not integrated, just we have expanded. Still we have not integrated, but just we have expanded this form. So instead of 2 into 3, we have 6 terms. Now we will integrate. So you see here, when I go to, from here I am writing here. So after integration it will become what? 2y squared by 2 delta minus 4y cube by 3 delta squared plus 2y power 4 by 4 delta cube minus y cube by 3 delta squared plus 2y power 4 by 4 delta cube minus y power 5 by 5 delta power 4 to the limits 0 to delta. I hope I can erase it now. So you try to apply the limits, 2 to get cancelled. So it will become delta squared by delta minus 4 by 3 delta cube by delta squared plus 2 into delta power 4 by 4 into delta cube. If you want, we can make it as 1 by 2 also, minus y cube, not y cube, delta cube by 3 delta squared plus 2 into delta power 4 by 4 delta cube minus delta power 5 by 5 delta power 4. Okay, so this 1 delta and 1 delta cube, so delta squared and delta cube squared here, delta cube and delta cube, delta squared and delta squared, delta cube and delta cube, delta power 4 and delta power 4. So finally I am end up with what? Delta minus 4 by 3 delta plus 1 by 2 delta, because I made 2 by 4 is 1 by 2, minus delta by 3. Here also I will make is plus 1 by 2 delta. Okay, this is also there. This is also 1 by 2 delta minus delta by 5. Okay, so I will erase this central part. Now we can make these two terms a single term, because this half, this another half, it will become 1. So it will become delta. I am adding these two terms. Half delta plus half delta will become 1 delta. So the remaining terms I will write minus 4 by 3 delta minus delta by 3 minus delta by 5. So it become 2 delta minus 4 by 3 delta minus delta by 3 minus delta by 5. So we can take the LCM as what? 15 now. 15 means 30 delta. 15 into 2. It is 5 into 4 minus 20 delta. It is 5 delta. Okay, minus 3 delta. So it will become what? It will become 2 by 15 of delta. Okay, 30 minus 20 means 10. 10 minus 5 is 5. 5 minus 3 is what? 2. So 2 by 15 delta. What is the left hand side? Theta. So we got the answer is what? The moment of thickness is 2 by 15th of the boundary layer thickness. Thank you.